Welcome back. In this video, we're going to continue recording our coding efforts on the binary trie. So this is where we left off. We were working on the leaf, and that's where we're going to basically focus to start with, is how to make it so that our leaf works as long as we don't need internals, because the original data structure is just leaves. I will also note that this test here currently passes because we do create an empty array sequence, and so the data length is 0. So we've actually made a passing test. Yay. This case we're not going to handle yet, so I'm going to put back in the 3 question marks for an unimplemented method. In this case, so how do we make an array sequence that's one bigger? And there are ways in which this feels like cheating. We take our data and we call this same append operator on E. That makes an array sequence that's one larger than what we had, because Scala has the built-in array sequence as an immutable array-based sequence. And I just need to make a leaf that wraps around that. And there we go. So this is what we want here. We'll come back to this when we actually have tests that are big enough to cause issues. Now, what about apply? So I can't really test my append. I mean, I can come over here and I can write code. So I can, let's go ahead and create an empty v1 equals empty colon plus, let's put in the value 7, and val v2 equals v1 colon plus a 9. And then we should be able to do an assert equals on v2 sub 0. The first value in it should be a 7. And the second value in it at index 1 should be 9. Okay, and we could write larger tests of this, and we will in a bit. But this is what we expect to work. But we should get interesting. We don't expect this to work. We expect this to have an unimplemented exception because our apply method isn't implemented. And I'll have to figure out what's going on with that, but we should look at the apply method. So what does the apply method do? Well, we have an array, and it's tempting to just say return data sub index. This is almost correct, but it's not quite there. And the problem is when the bvec is larger. So if we were to look at our drawing here, for example, v9, well, it has an internal node. But v9 has indexes 0 through 8. And if I get index 8, I'm actually going to come down to this node right here. I'll move this over so the lines don't intersect. I'm going to come down to this leaf over here. This only has one element in it. Index 0 is the only thing that's valid. So clearly I can't just take the index and go for that location. Instead, what I need to do is I need to pull off the proper set of bits, and we saw previously that we can do that by taking our index and downshifting it and then anding it. And so in our code, I want to take that index, and we'll throw some parentheses around this, and I'm going to downshift it, and I'm using the 3 downshifts. This is one that does not preserve sign. Because we want zeros to come in from the top. Now, people shouldn't be giving us negative indices, but it still feels more appropriate to me. So I want to downshift it by, well, okay, this is a leaf, so I don't need to downshift it at all. The internals all downshift. But I do need to AND it with something. Now, previously, I had made this 0xf, when it was 4 bits, or 0x3 when it was 2 bits. Representing this variable here makes it a bit more challenging. We could create another val that is closely related. It would be the value with all of the bits on. But how would we calculate that? So how do I make a number that has 2 bits on? And one way to do that is to start with a number that has all the bits on. And we can do that by putting tilde0. So tilde is binary negation. So it flips all of the bits for us. So it's 0 has all the bits off, tilde 0 has all the bits on. And then I need to downshift that, and here I will use the triple arrow because it turns out tilde 0 is a negative number. It happens to be -1, but tilde 0 tells us more about what's going on here. If I downshift it by 32, that would be all the way. I want to do 32 minus the bits in alphabet. So if we have, when this is 2, I'll downshift it by 30. We will leave 2 ones sitting there. If it's 4, we'll downshift it by 28, and we'll leave 4 bits sitting there. However much is left over, we AND with that bit mask, and that gives us back the index that we actually want in our smaller array here. So I'm still not certain about my testing. I'll have to go look at that, figure out what's going on, but we'll continue to write code and I'll come back with an explanation later. What about updated? So updated is setting the value at this location, at this index to that value. Well, here again, data has an updated method on it because it is an array sequence in Scala. And so I would love to have, it feels like that would be great, but we have the same problem that, and we need to make a leaf of this, but this code has the exact same problem that we had with apply, and that is that I don't just want to use the index, I need to use the index after the bit mask. And so we will copy that same code and put it here. This is something that we could wind up doing. Updated. Interesting. Okay, I will have to explore that one too. But we take this index, we're going to update it with that value and get a new leaf on this. And we can have code that does a simple test of that. Adding and setting, so I'm going to do the same thing here, but then I want to do val v3 equals v2 dot updated, where index 0 has been updated to 99. And then I can check that these things are true for v3. It is interesting. Note, I also want to go back and do the assertion that for v2, this is still 7. Now, in Scala, that testing isn't as needed because we're relying on the array sequence, which is itself immutable. But if I were writing this code in, say, Java, where I was using a raw array and it was very mutable, I'd want to make sure that I hadn't messed up my original value when I was doing things. I'd actually want potentially to do things here as well. In fact, actually, we could assert equals that the v1 dot size is 1, that this one is 2, This one is also 2. The thing is, to make sure we didn't mutate something, it's good to make sure that we didn't change the size of V1. Okay, so that gives us some additional tests in there, and we'll come back in the next video. I'll figure out why these things are unhappy, and we will talk about completing the leaf and then how to finish off this section of code right here where we need to go to an internal node.